Hello students. You're welcome to today's chemistry lesson. We'll be continuing our topic on the particulate nature of matter, part 2. In our previous class, we looked at physical and chemical changes. A physical change is a change that does not produce a new substance and can be easily reversed. Examples include the melting of ice or the boiling of water. A chemical change leads to the formation of one or more new substances and is usually not reversible. Example is burning of wood. We also explored the concept of atoms and molecules. All matter, everything around us, is made up of tiny particles called atoms and molecules. Next, we learned about Dalton's atomic theory. Dalton proposed that atoms are indivisible particles that can neither be created nor destroyed. Finally, we identified the constituents of atoms. Every atom is made up of three main subatomic particles: protons, neutrons, and electrons. These particles differ in their charges, their masses, and their locations within the atom. Our lesson objectives for today are to examine the arrangement of electrons around the nucleus, and how electrons occupy different energy levels. Next, we will explain the meaning of atomic number, mass number, and isotopy. Finally, we will learn how relative atomic masses are determined using the carbon-14 isotope as a reference. An atom is made up of three major particles: protons, neutrons, and electrons. The protons and neutrons are tightly packed at the center of the atom inside a region called the nucleus. The electrons move around the nucleus in fixed regions called shells or energy levels. These shells are arranged from the closest to the farthest away from the nucleus, and each shell can hold a maximum number of electrons. The first shell, known as the K shell, can hold up to 2 electrons. The L shell can hold up to 8 electrons. The M shell can hold up to 18 electrons, and the N shell can hold up to 32 electrons. This maximum capacity is not random, it follows a scientific rule. The number of electrons a shell can hold is calculated using the formula 2 multiplied by n squared, where n is the shell or orbit number. So, for the K shell, n equals 1. 2 multiplied by 1 squared gives 2 electrons. For the L shell, n equals 2. 2 multiplied by 2 squared gives 8 electrons. For the M shell, n equals 3. 2 multiplied by 3 squared gives 18 electrons. For the N shell, n equals 4. 2 multiplied by 4 squared gives 32 electrons. Electrons always fill the innermost shells before the outer shells, and this arrangement plays a major role in determining the chemical behavior of each element. Let's look at 2 examples. Hydrogen has an atomic number of 1, meaning it has 1 proton and 1 electron. This 1 electron goes into the K shell. Since the K shell can hold up to 2 electrons, it is not full. Oxygen has an atomic number of 8, which means it has 8 electrons. The first 2 electrons fill the K shell, and the remaining 6 go into the L shell. The L shell can hold up to 8 electrons, so oxygen's outer shell has 6 electrons. These are its valence electrons and they determine its reactivity. You're doing great, keep pushing forward. Now let's look at 3 very important ideas in atomic structure: atomic number, mass number, and isotopy. First, we have the atomic number, represented by the symbol Z. The atomic number is simply the number of protons inside the nucleus of an atom. This number is what identifies an element. No 2 different elements have the same atomic number. For example, hydrogen has an atomic number of 1, meaning it has 1 proton. Oxygen has an atomic number of 8, meaning it has 8 protons. Sodium has an atomic number of 11, so it has 11 protons. In a neutral atom, the number of protons is always equal to the number of electrons. So, atomic number equals protons equals electrons. Next, the mass number, represented by A. The mass number is the total number of protons and neutrons in the nucleus of an atom. The formula is mass number equals protons plus neutrons. For example, if a chlorine atom has 17 protons and 18 neutrons, its mass number will be 17 plus 18 is equal to 35. Let's look at isotopy. Isotopes are atoms of the same element that have the same atomic number but different mass numbers. This means they have the same number of protons but different numbers of neutrons. A good example is chlorine. Chlorine naturally exists as two isotopes. One isotope has a mass number of 35. The second isotope has a mass number of 37. Both chlorine 35 and chlorine 37 have 17 protons, but the number of neutrons is different, and that is what changes their mass number. Even though isotopes have different masses, they behave chemically the same, because they have the same number of electrons. However, some of their physical properties may be different. They may have different densities, or one may be radioactive while the other is not. Relative atomic mass, written as AR, using the carbon-14 scale. The relative atomic mass of an element is the number of times the average mass of one atom is heavier than 1/14 of a carbon-14 atom. Here is the formula. Relative atomic mass is equal to the average mass of one atom divided by 1/14 of the mass of a carbon-14 atom. By using carbon-14 as a standard, we can easily compare the masses of different atoms and calculate molecular masses, which is very useful in chemical calculations and experiments. Carbon-14 has 6 protons and 8 neutrons. It forms naturally in the atmosphere, and is used in radiocarbon dating to determine the age of organic matter, like wood or bones. Congratulations! You have completed this lesson. Now, let's test your understanding with some quick questions to review today's lesson. In summary, we examined the arrangement of electrons around the nucleus, and how electrons occupy different energy levels, such as the K, L, M shells and others, including how electrons are distributed within these shells. We also explained atomic number, which is the number of electrons, and mass number, which is the total number of protons and neutrons. We discussed isotopy, which refers to atoms with the same atomic number but different mass numbers. We further learned that relative atomic mass, based on the carbon-14 isotope, is the average mass of one atom, compared to 1/14 of the mass of a carbon-14 atom. I am confident that you found the lesson exciting and engaging. In our next class, we will discuss symbols, formula, and equations. Thank you.